Hello. Today we're going to continue with our work with linear equations, but to begin, let's take a quick look at what we've done so far. So remember, the structure we're going to use for a linear equation is y equals mx plus b. This is the way we represent the relationship between two variables, and usually we use x and y as the variables to represent those two things we're analyzing. In the past, we've looked at how much salt versus how much honey is in a recipe, or how many hours versus how much money was made at a job. So those are types of variables that you can relate to each other in a linear relationship. Now, the m, remember, is super important. It is the steepness of our line, or the rate of change of our line, that helps us compare x and y. Okay? And then b, we use the letter b to represent the initial value. So it's the y-intercept. It's where our line would technically cross the y-axis, but in terms of the problem and the context of a problem, we said that the y-intercept is the beginning of the problem. It's the initial value, what we start with, right? So we've seen that before. We've been working with that. We're going to need that for today. Well, let's think a little bit deeper about this. Let's think of what we mean, first off, by a solution to a linear equation. What does that mean to have a solution? And is there only one solution? Could there be multiple solutions? And then also, how can the graph, which we've been working with, the graph of linear equations, how does that graph represent or play into this idea of a solution? Can we see the solution on the graph? Can we use the graph to help us find solutions? So let's take a look at a specific example. Going to a corner produce market, going to the store, we see that apples cost $1, oranges cost $2. So let's try and find the cost of a combination of apples and oranges. Let's use 3 apples and 4 oranges, okay, just to start off. So let's see if we can model this with an equation and then see how we can use the equation to find the answer to this question. How much would 3 apples and 4 oranges cost? So if we take a look here, remembering that each apple is $1, each orange is $2, 3 apples would be $3 total dollars, right? Oranges would be $8 total dollars. All right, so together, in total, you would have $3 and $8, which would be $11. Great. We didn't really use x and y at all in that situation. We didn't really define a linear relationship there at all. We just calculated how much 3 apples would cost and how much 4 oranges cost based on a price. So let's see what we really did, though, in terms of an equation. So if we let apples be x and oranges be y, let those two things be represented by x and y. We could switch that if you wanted, but let's just try and keep it the same, x and y. We could represent this situation with this equation down here. We can see that 1x represents $1 per apple and 2y represents $2 per orange. The sum of those two quantities would equal the total cost for any given combination of apples and oranges. So it's kind of cool. We just created an equation that represents infinite combinations, all right, infinite combinations. Now, we don't really need to calculate infinite combinations of apples and oranges, but let's say we wanted to know how many we could get with $10, right? We could figure out all the possible combinations of apples and oranges, given their price, that would lead to $10 in total cost. So how do we incorporate that 10 into our equation? So we have an equation, 1x plus 2y equals total cost. What we're going to do is substitute our 10 for total cost, and we'd end up with the equation we see here. 1x plus 2y equals 10. Now, this equation specifically gives every possible combination of apples and oranges that lead to $10. Okay, so we've put sort of a cap or a roof on how much we're going to spend. So it limits how many combinations we can come up with. And you got to keep in mind, we're probably not going to cut the apples up into pieces and try and get half an apple. Store probably wouldn't be very cool with that. They're going to make us pay for the whole thing. So we're going to be working with positive integers here. We're going to look for positive whole numbers. Okay, so if we use this equation, for instance, to see what if 4 apples and 3 oranges would work, what we do is substitute 4 in for x, 3 in for y, and we'd simplify. So we'd see that 4 plus 6 equals 10, right? 2 times 3 is 6. We'd see that that combination works. 4 apples, 3 oranges will reach a total of $10, and we'd be good. We could pay for that. One super important connection here is we're substituting values for x and values for y and trying to see if they will make a combination that would equal our total. We also know, and we're very comfortable with using x and y to graph, right? X represents our horizontal motion, y our vertical, right? So when we have a solution which we just found, 4 and 3, are solutions to this equation. They make the equation true, which is what a solution is. We can think of 4 and 3 not just as apples and oranges, but as right and up. So 4 comma 3 is now a location, all right? So really interesting idea that these apples and oranges have now turned into a starting point for potentially a graph. So let's take a look at this. Here's a graph of the equation 1x plus 2y equals 10. And you can see the little red dot here, that is the point 4 comma 3, which we found to be a solution to this problem. 4 apples and 3 oranges resulted in a total of $10, which was something we wanted to do. But that means that every single point on this line, every single point from here, 0 comma 5, to here, 10 comma 0, are all possible combinations of apples and oranges. But we all know, as we said, we can't talk about half an apple or a quarter of an apple or an eighth of an orange. So we're only going to look at our whole numbers, like 1. So if we look at 1 apple, we see that that results in, 4.5 oranges. That's no good. We don't want to cut an orange up. So we're going to move to 2 apples. And there we go. We see that results in 4 oranges. Or let's say we really like oranges. We could buy 0 apples and end up with 5 oranges. Or on the other side of the coin, we could say, I don't want any oranges. I'm just going to get 10 apples. All right. So this is the big picture here, is that this graph, which is a graph of the linear equation we created about apples and oranges, relating them, is actual visual representation, a visual representation of every combination of apple and orange, or more importantly, X and Y, that make this equation true, satisfies this equation. So now in the future, we need to solve an equation, especially if it's pretty tricky to work with, algebraically, manipulate, move stuff around, all the stuff we've practiced. We can just throw it up on a graph, throw it into Desmos, take a look at the picture, and find out what we need. So if I were to ask you real quick, hey, how many oranges am I going to get if I buy 6 apples? You're going to go to 6 on the X, because you know you have 6 apples, and you're going to see that correlates with a Y value of 2. And since Y is oranges, that means you get 6 apples, you're going to get 2 oranges. Okay? So pretty cool how we can find solutions, which again are the values that satisfy an equation, that make it true, by just looking at the graph of that equation. Okay? So to wrap that up, today we looked at how a graph of an equation in 2 variables is really just a visual representation of the set of all solutions to an equation. We saw that there's answers to this problem that don't really fit our context, right? We're not going to take negative apples, not going to take negative oranges, and we're certainly not going to take fractions of the fruit. We get in trouble for that. I've tried it, don't do it. So that's a wrap up for today.